Jessica, I really appreciate you coming on and being willing to share your work with the audience. To start, can you tell us a bit about your academic background and how you got interested in analytical chemistry?
Absolutely. I have my chemistry degree from Thompson Rivers University, TRU, in Kamloops, British Columbia. It was a Bachelor of Science with a major in chemistry and my minor in physics. I got into analytical chemistry probably my second year of university in Dr. Kingsley Doncourt's class. That's when I learned how many numbers were in chemistry. And I'm a big number person. I love to delve and go straight into the nitty gritty details. And right from that moment, I loved analytical.
Was there anything that drew you to environmental water analysis in particular?
Yeah, right at the end of my first year of university, I started working at a pool and hot tub store as my side job. And through the training there, over time, I gained just more of an interest in water chemistry because I got to test the water at that facility. And slowly through there, I started just loving more and more of the details of water chemistry. And then I got to meet Dr. Sharon Brewer, who was my undergraduate supervisor. And that's one of her specialties, and it just fell right into place.
Very cool. I know today we'll be talking about haloacetic acids, and I'm not too familiar with them personally. Would you be able to introduce those to the audience?
Yeah, haloacetic acids, or HAAs, they're a form of disinfectant byproduct, or DBPs. And the disinfectant byproducts are formed when there's organic matter in the water and it's interacting with the sanitizer used to form those DBPs. Some of them can be a little harmful, which is why haloacetic acids are one of the ones that we like to look into.
My understanding is that most labs rely on somewhat standard EPA methods for HAA analysis. So, what are some of the practical limitations of the methods that you run into as an undergraduate researcher?
Yeah, I had a problem with my EPA method that I wish I could have used. It only worked for GC-ECD, and my university just didn't have access to that instrument. So that then falls into the place of how do I even look for my haloacetic acids? And there's no EPA method that I can use that has the instruments that I have at home. And then, of course, even if I did have the instrument, if there's graduate students that want to use it, I fall back in the line at the very end.
I believe you relied on a GCMS method using dispersive liquid-liquid microextraction. So, what initially attracted you to that approach, or was it because that's what was available?
GCMS was what was available. I ended up finding a wonderful article by, I believe it was Al Shatir, that had a very similar idea to what I wanted to do, so I could adapt it slightly to my method. And for the microextraction, that was Dr. Brewer, my supervisor's idea, because it's not something that we do in the undergraduate laboratory courses. She thought, that'd be a great experience for you. Let's try that.
Now, I know that HAAs are non-volatile. Can you walk us through why derivatization is necessary and how you approach that in your method?
Yeah, so with GC, we do want some volatile components just because it all has to do with our boiling point. We need it to be in a gas. So for HAAs to be non-volatile, that made it really difficult to even use a GC in the first place. But I ended up doing a derivation with octanol. That way it had a lower boiling point, which made it more volatile, and also it was a slightly larger fragmentation, so it's a little bit easier to help pick out the fragments from each other with that longer tail.
And it sounded like you spent a fair amount of time optimizing the GC temperature program. What were the biggest challenges in getting clean separation while keeping the run times as reasonable as you could?
My biggest problem was honestly the octanol. It created such a large shoulder that, and it was such a late shoulder, it was in the 6 minute mark already. And I had so many samples to run, I didn't want a very long program. So that octanol, even though it ended up being very useful, for the derivation, it ended up causing a lot of problems with the separation because of just how long the shoulder was.
Yeah, I mean, that was an interesting question, I thought, in terms of the analyte or peak that caused you the most trouble, but it sounds like that's what it was.
Oh, the analyte was the monochloroacetic acid.
Mm.
It was just because it only had the one chlorine difference, it just blended into the octanol peak. And I could see that there were some chlorine fragments in that peak, but I couldn't quite pinpoint exactly where it was. So that one caused me a little bit of trouble.
And certainly every new workflow, I suppose, is going to face its own challenges. The main audience of this podcast is academic researchers like yourself, and especially for the early career scientists just starting out. Could you talk about how rewarding those early successes were in terms of maybe that first analyte peak and how important that is to build the confidence of a young researcher?
Absolutely, yeah. That when I found my first analyte, I remember it so vividly because our GCMS, it's in a separate little room in the lab. And I was just working away, looking at my little fragments, and I find something that actually looks like my analyte. And I'm doing a little dance in my chair. I'm doing a little jumpy dance, celebrating. And I didn't think anyone else was in the lab to see it, but then the lab technician walked in and he also got excited because I was excited and we were just dancing. It was just so rewarding getting that little bit of joy to keep going on.
I know in terms of your findings, there were some of the conclusions that were unexpected in terms of the HAAs and specifically the chlorinated ones. Could you comment on that?
I was expecting mostly chlorinated HAAs. I was looking at, of course, chlorinated and brominated ones. And all the samples that I analyzed were sanitized with some form of chlorine. 4 of them were sanitized with sodium chloride through electrolysis to create the chlorine ions. And then some other ones were using a type of chlorine puck that are used in pools and hot tubs. And you would think that means a lot of chlorine. Somehow I had higher bromine HAAs, which confounded me for a while. I did know that there is often bromine contaminants in the typically pool and hot tub chemicals, even if it's mostly chlorine. With that in mind, I thought it would be lower bromine, but I guess I would need to take a peek into the actual chemicals to see what content of chlorine and bromine are in them.
Now, I know your part-time job helped create some interest from you personally for this project, but did any of that work experience from the part-time job give you an upper hand in terms of your familiarity with the project, if that makes sense?
Absolutely. By the time I finished at the workplace, I was there for almost 4 years. It was because of that I had access to all the SDS sheets that the chemicals were used in my samples, because all the samples I took were from people that went to my store as clients. So I knew exactly what they were adding to their pools and hot tubs. I knew exactly when they were doing it. And it definitely gave me a leg up because I knew the exact chemicals that they were using.
That's even better than I thought, honestly, in terms of how much of a advantage or extra step forward that background information gave you. We talked about the difference in the application that you had in your workflow versus the EPA method. Would you say that the GCMS adapted approach yielded any advantages over the standardized method?
I found it was so much faster compared to the standardized method. I did try a very similar approach of the standardized method that was adapted by Chevelli, and it's a 2-hour water bath. I think it was probably like a 30-minute run time for each sample in the temperature program. And then with my adapted method, my wait time for the derivation was only 10 minutes. So the biggest thing I noticed was that with the method I got to use, I could get all my samples going have the temperature program set, auto sampler going before lunch. And then with the EPA method, I would have to wait for the derivation during lunch because it would take all day to get it ready.
Well, that's great to hear there was some advantage to doing it your way rather than doing the best you can with the instrumentation that you had available and then feeling like you were in a worse spot. So, bringing everything forward to today, you're at the University of Calgary now and working on a completely different project focused on ozone and nanobubble disinfection. Are you able to connect your current work with the old project at all?
I can connect the general things. I managed to get this position because of the work that I did with the haloacetic acids. Having that background in the disinfectant byproducts is what drew me to the Chromatography lab at the University of Calgary. She ended up wanting someone with a little bit of history in the disinfectant byproducts, and it just ended up being a perfect fit, so I can bring that knowledge forward with me. And I want to keep looking at water.
Yeah, just to let you know a little bit about my company, Organimation. So we manufacture the blowdown evaporation equipment. So we're coming in after the extraction step. If you're familiar with any of the EPA water quality methods, you're doing a solid phase extraction and then you're evaporating to dryness ahead of LCMS. So that's where the products are used. But one thing I think is really cool about our equipment being used in a lot of the environmental contaminant methods is you really feel connected to worthwhile work. And that's kind of what I hear when you talk about, oh, I'd still like to really be doing water analysis in the future. One thing that was very cool about your upcoming or current work is you'll be able to use a different analytical technique in terms of ion chromatography. Could you talk about your interest and excitement doing that?
Yeah, I only got to use IC a couple of times during my undergraduate degree. So being able to step into what feels like a completely new instrument, I've already been sitting down with my mentors and running through how to run it, and I'm hoping that I'll be able to start doing research on it pretty soon here. But, and also, of course, delving into nanobubbles is completely new, and the amount of papers that I've been able to read on nanobubbles and ion chromatography working together has been great.
Very good. Yeah, I suppose in some ways that's the absolute best thing you could do before you get that hands-on experience with the new workflow and new application. As I mentioned, the audience of this podcast is academic researchers like yourself. Based on what you've experienced, do you have any advice maybe for underclassmen who are just starting their journey in analytical chemistry?
Yeah, I can say what Dr. Brewer always told me when I was going through my research. Bad results are still results. It's okay if you get a little frustrated when you get bad results. As long as you know that at the end of the day you have some results, you can still publish them, and you're still learning from them.
That's great advice. Yeah. Regarding the HAA analysis project, was there anything else that you thought the audience should know about your work?
That's a good one.
I suppose some pool or hot tub owners, is there any takeaways for them?
I can say, generally, based on my results, don't drink out of your hot tub. You already shouldn't be, but also a note for especially young kids, because young kids will drink out of anything. The results that I got, the HAAs were higher than the federal regulation. Of course, we're not monitoring hot tubs and pools because we shouldn't be drinking out of them. There was one of them, I think, it was over 100 parts per million of haloacetic acids in one hot tub. The federal regulation is 80 parts per billion. So it was a big jump. So I guess the general takeaway, already shouldn't be doing it. Don't drink out of your pools and your hot tubs.
Not to throw you a curveball that I didn't tell you what I would ask you, but offhand, do you happen to know what would be the result or impact of ingesting HAAs? Is it just that you'd get very sick, or are you aware of any specifics?
Yeah, there's 3 that are labeled as probable causes of cancer in human. I think it was dibromoacetic acid, bromochloroacetic acid, and there was one more that I'm forgetting out of the main 6 that we test for. And I believe, off the top of my head, it was a high chance of tumors. It was either liver or kidney. But that's, of course, with extensive drinking of it.
Yeah, regardless, you just have to remember the general advice of not ingesting it. Well, Jessica, this has been really awesome. It's a super interesting project, and always happy to learn, especially more about GCMS as it relates to environmental contaminants, because it is such a important application, certainly one of the main analytical techniques that people who are doing analytical chemistry are exposed to. But yeah, thanks so much. I really appreciate your time, and as you work at University of Calgary, if you ever want to come back on and talk about your next project on ozone, I'd appreciate it.
Yeah, thank you so much for inviting me on.